So thanks for organizing this seminar and inviting me here. This will be a very leisurely talk. There is a result in this talk, but most of the talk will be about why this is an interesting result and not about the result itself. And the intended audience are harmonic analysts who don't know too much about stochastic analysis. If you know everything about stochastic analysis, you will be bored. Also, questions are welcome. If you want to ask a question, please interrupt me immediately. You can also try to write down the slide number and ask the question later, but you can just as well ask right away. We should have plenty of time. So here is the two-line summary of this talk. I claim that stochastic integration is the same as paraproducts. And in stochastic analysis, people like to use continuous time, but I claim that continuous time is the same as discrete time with good estimates. So there is nothing, you don't need any fancy technical setup to understand continuous time if you just understand discrete time well enough. Okay, so what is stochastic integration? Why do we need it? So here, G will be a sample path of a stochastic process. Here on the right, you have some examples of what it may look like. These are Brownian, fractional Brownian motions with various Hurst exponents. And okay, the Hurst exponent is basically the same as Hölder exponent, and the smaller it gets, the rougher it looks. Okay, and let's say we want to treat ordinary differential equations. This is the simplest kind of equations for us. And let's say we have this very simple form where the increment of the unknown function f is proportional to the given function g with some factor that depends on the solution. Now, of course, this doesn't really make sense the way it's stated, because these differentials here, I mean, these functions will certainly not be differentiable, so you cannot interpret it with differential forms or anything. So the usual thing that you do when you cannot interpret your equation is make a weak formulation. And you remember from your introductory classes that this is also how you prove existence of solutions to ODEs. You write some integral formulation. So, okay, here's an integral formulation, and we still don't know what it means because we don't know how to integrate with respect to dg. dg is not a measure. If g is merely Hölder continuous with exponent less than 1. So the question is, how do you interpret this integral? And one answer is you just look at Riemann-Stieltjes sum and see whether they converge or not. And here is a very simple situation. I just take some sequence of some partition of the interval and then partition each interval into 2 and look at the difference between the sums for the final partition and the coarser partition. And if you do some algebra, then you can rewrite it in this form, where you have increments of your coefficients a and of the integrator g. Now, we want here to take the integrand a always on the left end of the interval, because we want these to be predictable somehow in the integral. This is so this is kind of Ito integration. Anyway, and what comes out is this difference here on the right-hand side. And here, these are consecutive elements of a partition. So we can, if we assume that both A and G are Hilder regular with exponent alpha, then each of these terms is bounded by this difference to the power alpha. Yeah, by the way, why should we assume that A has the same regularity as G? Well, that's because if we look at the simplest case, let's say A identically equal to 1, then the solution should be F equals G, or maybe G minus G of 0. So F, the solution F certainly can't be more regular than G, so we say they have the same regularity. All right, so we get here this power 2 alpha, and now we just sum over all blue intervals here. So this sum will go to 0 when we let the mesh or the maximal length of the interval in the partition go to 0, if and only if the regularity exponent is greater than alpha, is greater than 1/2. So if this is satisfied, then this goes to 0 when mesh of the partition goes to 0. All right. Now this, of course, doesn't, so this works for more regular processes, but this doesn't work for those here. And in particular, it doesn't work for martingales. So this is the Brownian motion. It has, it's Hilder continuous with exponent, with any exponent strictly less than 1/2. So, okay, the question is, what do you do instead if your integrator has less regularity than 1/2? And basically, so we want to define this integral, and we have two options. Well, maybe there are more, but these are the two common options. We need to use something more about our integrator, or maybe also about the integrand. And one option is we use some orthogonality, and this will be stochastic integration. So if G comes from a martingale, so if G of t is a path of a martingale, then the increments of G are orthogonal, and then we gain a square root in the sum of the things that we look at the previous slide. And this is stochastic integration. So the other option is to use algebra, and this means that we replace Riemann sums by better approximations, well, hopefully better approximations, some higher order quadrature rule, and hope that then our sums converge to something when we let mesh go to 0. And if you do this properly, you get what is called rough integration. So there are also names attached. Stochastic integration is eta integration, rough integration is bivalence. Okay, so let's start with the first option. That's stochastic integration. Let's take, well, here I assume that it's a Kadlec martingale. Don't worry too much about this Kadlec assumption. So the quantitative assumption is that the martingale maximal function is an L1, and we have an adapted process A that we want to integrate, and this one is bounded uniformly in space and on the probability space. So now that we have a martingale, we also have a probability space. So G and A are defined on some probability space times the time interval and take values, let's say, in the reals. So the way you define the Ito integral is you take an adapted partition. So an adapted partition is just an increasing sequence of stopping times, let's say, starting with 0, and each tj is a stopping time. And then you just write down the Riemann sums, and it turns out that this does converge if you let, so in which sense does this converge? This converges along the directed set of adapted partitions. So adapted partitions are ordered by inclusion. So if you have a finer partition, then it is larger than a coarser one, and along an ordered, right, this is a directed set with respect to inclusion order, so you can define a limit along it. Okay, and why does this work? Well, there are a few reasons or a few points that make this work. One is that this right-hand side here is bounded, or the mapping from G to this right-hand side defines bounded operator on, let's say, martingales with L1 maximal function by the BDG inequality. BDG is an standard abbreviation for Burkholder-Davis-Gandhi. So if you just write the L1 norm of the right-hand side, then the important part is that these differences are also a martingale. So the L1 norm of the right-hand side is by the BDG inequality comparable to the L1 norm of the square sum. Yeah, okay, I will write this down. Square, 1/2. And then you can pull out the A, and you get the square function of this stopped martingale G, index T, and that you can compare back with the maximal function. Okay, but now how do you actually show convergence? Well, you need to exhibit some partition which brings you close to the limit, and this is the partition. It's just a greedy choice. You stop each time when your integrand changes by at most epsilon, and this gives you an adapted partition. And if you choose any finer partition, T tilde, then you can write a similar formula as here for the difference of these two expressions, and you will get a gain from the fact that you will have a difference of processes A stopped at different times here, and these differences will be almost always bounded by epsilon. So when you pull it out, you will get a gain. All right, so this shows that this right-hand side is a Cauchy net. In many stochastic analysis textbooks, they for some reason like to use deterministic partitions, which make this whole argument much messier. But if you just use adapted partitions, it's very easy. So we have constructed the stochastic integral, and we have proved some trivial LP estimates, but we are not done here because these are not the best estimates. And so one can ask, what are the most useful estimates that one can show for stochastic integrals. And to understand what is useful, we have to look at the other approach to integration, namely rough paths and rough integration. So this is our second approach to defining what it means that f is an integral of a with respect to g. So recall that we already looked at, I have indicated that this integral can be defined with Riemann sums if a and g are sufficiently regular. And in this case, there is also a different characterization of this integral, namely by kind of fundamental theorem of calculus, namely that the derivative of f with respect to g should be a. But now one has to be careful with what it means. So f can be approximated by a linear function of g with coefficient a. This is what it means, that a is the derivative of f with respect to g, and then there is an error term which should be of smaller order, and in this case it will be bounded by the length of the interval to some power greater than 1. So this is important, that this power is greater than 1. For instance, this immediately shows that there is at most one function, f, that satisfies this property. If you had 2, then their difference would be Hölder with exponent strictly greater than 1, and therefore constant. So how should one, or what should we replace this with when the regularity is less than 1/2? So here is the answer. If we want to define, or if f is the integral of a with respect to g, then we can also look at a higher order expansion of f with respect to g. So a will still be the derivative, and b will be now the second derivative of f with respect to g, or formally the derivative of a with respect to g. So if we have such a derivative, then we formally would expect the following expansion. So now we have a second order approximation, so that we get here a higher order term than there. And now the order here is large enough that this exponent is greater than 1 in a certain range of exponents, which will be the one I will talk about today. This is now a reasonable definition, because at least with this property characterizes function f up to a constant, which is immediate, because if you have two different f's, this will force their difference to be Hölder with exponent greater than 1. So this is a reasonable definition. The other question is, of course, whether such an f exists, and it does not in general for general a and b. In fact, you need a relationship between a and b, which is some discretized version of this b being the derivative of a. But let's not dwell on that. Under some suitable conditions, such integrals were indeed constructed by Lyons. Now, another thing I would like to mention is that what I said previously was true for scalar functions, but it doesn't work exactly like that for vector valued functions. Of course, the first problem with vector valued is that you have to define what you mean by various products. Maybe A is some operator valued thing so that it maps some vector value, some vectors from the space in which G lives to the space where F lives. Then the derivative of A will be a bilinear operator. And now you can apply it to a tensor product. But the more important thing is not that you have a tensor product here, but that this expression here looks a little bit different from what we had before. So before we had something like this: T minus GS squared. But the appropriate thing to put here, it turns out, is this integral, which one can also write formally as an integral of u greater than, let's say, v greater than s less than t, dgv tensor dgu. So this is like an integral of a triangle. And previously we had such a square half, and this square, of course, consists of two such triangles. But if G is too rough, then it does not actually consist of two such triangles because there is some stuff going on the diagonal, which makes these two things different. So the correct thing to put here is actually this kind of integral, and not just a square. And this integral is not an algebraic function of this first order increment, so it's not this. And this was pretty well known in numerical analysis. So there were people who were investigating all possible higher order methods for solving ODEs numerically. And there is a whole theory of what kinds of integrals you need to get some higher order approximations of ODEs. And okay, in that period, they did it for smooth functions, and for rough functions, G. This may be not defined, but if you do have some way of defining it, this second order increment, then you can use it to integrate other things against G. And this was figured out by Lyons, and there is a substantially improved theory by Gubinelli, which clarifies what kind of A and B you can put here. All right, there's also multidimensional versions of rough integration. So here we are integrating in time in one real variable, in several variables. There's Heider's reconstruction theorem, which is a kind of generalization of rough integration, although not quite. So I have a recent paper on arXiv about Heider's reconstruction theorem, which also explains what's the difference between the two. Okay, so to summarize, there is a problem here because we need this integral, this second order increment of G in order to get started. But if we have this integral given, then we can go from it to any other integral A with respect to G. So since we need these two things, g and the second order increment, to define our integrals, we collect them in a single object, and this object is called a rough path. Actually, you need some quantitative regularity of these two things, g and the second order increment. And now let's talk about what kind of regularity you can put on them if you want the theory to apply to martingales eventually. So the answer is you can measure the regularity in p variation. Here is the definition of p variation of a path. It's the supremum over all increasing partitions of your time interval of the increments of the LP norms of the increments along this partition. So there is a simple estimate that the p variation is bounded by the Hölder norm. So you get this by estimating this difference here by the length of the interval on which you are looking for the increment. And then these two powers cancel, and you see how it goes. So it is quite like a Hölder norm, but it is parameterization invariant. And it works well for martingales because for a general martingales are parameterization invariant, so it doesn't make sense to use anything which depends on parameterization. Okay, now with this measure of regularity, you have Lipanger's inequality, which says that the p variation of any martingale is bounded in LQ norm by the maximal function with respect in the same LQ norm. Okay, and this was proved by Lipanger. There were different or better. So Lipanger proved this in L2, and then he had some qualitative argument extending this to LQ because he didn't have good martingale inequalities at his disposal. Then Pizier and Chou proved it, and Bourgain proved it with real interpolation and better martingale inequalities with good constants. And in the end, I will show you a very simple proof for this inequality, which also gives Q equals 1 because it doesn't use interpolation. Now, with Lipanger's inequality, you might have seen it applied in some harmonic analysis contexts. You can transfer it to various things, various operators. Radon transforms, there is this Fourier restriction thing of Vieco is here. Well, there are many different things you can do with that. For us, this just says which regularity we should use for our rough paths. So what about the second component then? So the first component was G, the path of a martingale. Then we have this second order increments, which I denote by this Blackboard bold G. This is also the reason why I use this particular font for this presentation. It has this symbol. Okay, and it is quite obvious what should be the p variation of that. Namely, you take any increasing sequence, and since this has two arguments, you can just put this increasing sequence in the two arguments and take the LP norm. What is maybe less obvious is that you should take the p half norm instead of p. Okay, and there is an additional algebraic constraint that this second component of a rough path should satisfy. So it's set up in such a way that if G, if this second component if is of a form integral g dg, then it satisfies this algebraic relation. Okay, and now you can define the integration along a rough path. For this, you need the first and the function that you integrate and its first derivative. And the integral is just defined by having this kind of expansion. So it is a second order expansion, and there is some error term which is now okay, it has somehow better regularity. I will not dwell much on what this means, but it just means that it's better than the other terms. Also, of course, we need an algebraic relation between this B and A. Well, actually not algebraic, it also involves an inequality, but it somehow generalizes the fact that B should be the derivative of A, except that now we are in the Hölder scaling, so it's actually something involving Taylor's formula with a little bit unusual error term. Okay, so what can we say now about our martingales? If we define the second order increments by this formula that I had before, with a small modification that we put here a u minus, because we want predictable integrands in our E2 integration. Never mind this distinction. So what we know is that these things will be indeed bounded in p-half variation for any p greater than 2. So this was proved independently by Cheverev and Fritz and Wieck and myself. And there were some, essentially this is not very hard. This was just adapting previous proofs and making them more careful. Particularly, this was a very useful result where this was proved for dyadic martingales. Okay, now there is a more general version of this result, which does not assume that the first or in that previous result we were integrating martingales against martingales, but we can integrate any functions against martingales. So this is the main quantitative estimate of this talk, the one that's in the title. So everything is a paraproduct, and well, what is a martingale paraproduct? So you take a martingale G and an adapted process H, and you multiply the increments of a martingale by something predictable. But it turns out that the correct, so what you may naively put here is maybe just H at time J minus 1, but it is much better to put here such a difference. H at time J minus 1 minus H at some previous time. And then consider this as a process depending on two time variables, S less than T. And then one can show that this is bounded R variation under, well, natural homogeneity assumptions on the various exponents. And the most important is this one, which is already highlighted. So in typical applications, if H itself is a martingale, then this P equals 2. And then we can put here R as this exponent, any R greater than 1. and then this recovers the previous result. Or we can take h, or we can take p equals infinity. That's maybe the other thing that is sort of interesting. And then this is a more usual product. No, then this is like a Martingale transform, right? Now here I've stated this in a little bit simple setting. There's also a more general version of this result where instead of this difference, we have a process which depends on two time parameters. And then there's a similar estimate like here, but we need some structural hypothesis on this two parameter process to make this work. And this is not an idle exercise because this structural hypothesis is in fact interesting because of so-called branch graph paths. This is what you need when you work with graph paths of regularity less than Herder 1/3. But I will not go into detail about that. All right, and to round things up, a few quick consequences of this estimate. One is how do you construct Ito integrals? I mean, at some point I said that that we had an estimate for Ito integrals, but in fact we have estimates for discrete things, and these estimates in particular imply existence of Ito integrals as well as proven bounds for them. And in particular, this shows that if you greedily stop the integrand like this is the same condition that we've seen before. As soon as the integrand moves by epsilon, you stop. This gives you an adapted partition, and then you can define a stopped process f by making it constant between the stopping times. And then it's easy to define this right-hand side. This right-hand side is just a finite sum because there are only finitely many different values of the integrand. And these finite sums converge to the, well, converge as you let's say this parameter go to 0 in some pretty reasonable sense in an LQ of a probability space with values in some R variation space. This is a pretty nice mode of convergence. All right, and for stochastic analysts, we also have some results like this with Herder norm instead of variation norm here. Although there it's not a convergence because this, well, anyway, we have estimates for this limit in certain Herder spaces with some moments around it. But I guess this is not so interesting for this audience. Another thing that we can do are joint lifts of rough paths and martingales. Previously, I mentioned that if we have a martingale, we can lift it to a rough path consisting of a martingale itself and some second-order increments. But what if we also have another rough path? Then we need more components in the term, and well, we can construct them all. So when would you want something like this? Well, maybe you want to solve an equation like this, where H is something deterministic but very rough, and G is a martingale, and you want to solve an equation like this. And Hoa, who is in the audience, has another way of doing this, which is in some situations better. So if you're interested in that stuff, also consult his work. But if you want the rough path approach, then this is the way to go. We start with G and H, and then we construct a joint lift to a rough path, and then one can make sense of this equation. The additional work in this with respect to what I said before is that one needs to define this thing. This is essentially a partial integration, but as I said before, partial integration in stochastic analysis is not, it's a little bit more difficult because you have, you divide the square in which you integrate two triangles, but there's also something non-trivial going on the diagonal. All right, this is almost it. Now, this talk also has a small proof. It literally fits on one slide. How do you prove Lipanger's inequality, which I stated before, and I'll also repeat here. The inequality is there on top. Okay, this color is not very visible. This is the inequality. Well, this is a very simple stopping time argument, which is a little bit like a Rademacher-Mitschoff argument, but the stopping time here has to be suitably adapted to our process. So this looks maybe a little bit like the construction and Davis decomposition, although not really. Anyway, so we want to show that the p variation is bounded by the maximal function. Well, let's define the infinity variation, which is just the maximum difference up to a certain time n. And then let's define a sequence of adapted partitions. For larger m, these partitions will capture smaller oscillations of the Martingale. And the definition is really simple. We stop as soon as our difference from the previous stopping time is larger than a fixed factor times this L infinity or this infinity variation at the time when we stop. Okay, and then there is this parameter 2 to the minus m to account for different scales. And it turns out that if we do this, then we basically capture all the possible jumps of our process. So that this sequence of partitions basically gives you kind of the best. Well, if you measure R variation, here you are only allowed one partition. But the problem with that is that this partition may be not a stopping time. And so here we replace this by countably many partitions, but these partitions are now also stopping times. Here we have many partitions, but they are stopping times. Well, we can also call them adapted. Okay, and then we can just estimate a little bit of this power here by the supremum.
Pavel, and why is this first inequality true?
Well, this is a greedy construction. Well, you have to think a little bit about it, but this is a greedy construction. So basically, if you have a jump of a certain size, then you will certainly pick it up for some m. Yeah. So you take any partition and look at a certain jump, and for some m, you will pick up a jump of that size at that location. That's all. Okay, and now you can just pull this out and estimate the remaining thing. So the remaining thing is just a square function. And okay, this finishes the proof. So this you pull out, and this is a maximal function. What remains is a square function. Okay, there is again some silly bootstrapping argument that you first need to make this for finite martingales with finitely many times so that you can do this. But anyway. So okay, here you get a square function bound by BDG inequality. That's it. So there is a funny little problem here. You can compute that this works if you replace the LP in the definition of this P variation space by something like L2 log L to the power 1 plus epsilon. There's a question whether you can do L2 log L, because this is what you get for the Brownian motion. Anyway, I would also want to say a few more words about the other theorem, the one about para products. The general outline of the proof is kind of the same. So you start with stopping time, which is basically like this. But then you get here something more complicated. So at this stage. And to handle it, one has to use not much more complicated, but things, namely just vector valued versions of this usual Martingale inequalities. And these are basically well-known things. We can prove them with classical tools like Davis decomposition and good lambda inequalities. I would just like to mention that there is also a proof using the fashionable tools, namely weights. There are proofs for all these things using weights, and so the first weighted inequality that would have been useful here was proved by Dameleva and Petramichel, who showed that Martingale transforms are bounded on L2 with A2 weights. Now, but there are also A1 even estimates for in Burkholder-Davis-Gandhi inequalities, and one direction was proved by Sikovsky, and he also proved the other direction, but with a caveat that the weight has to be continuous in time, which somehow makes it useless for interpolation, extrapolation. And so I removed this with a student of mine. There's even a nice constant here, 2. Without the weight, it would have been square root of 3. This 2 might be sharp. That's all for today. Thanks for your attention, and I welcome more questions.
Thank you. I'm going to pause the recording for questions.